So what is vector valued function? So it looks like this. This is a vector which depends on t, and you have three coordinates. Each is a function of t. Or you can rewrite this as f of ti, g of t, j, h of t. Okay. So what does that mean? For each value of t, you get a position vector of a point. Okay. So an example. So this is a three-dimensional vector. A two-dimensional vector would be just two components. Okay. So let's do an example. I'm just making up an example. R of t is, let's say, 2t, 3 is t squared minus 1. Okay. So each value of t, you get a point in the space. So here the domain of t, so t can be any value, right? For any value of t, this is a vector. So the domain for t, I mean domain for the function r, which is the domain for t, is negative infinity to positive infinity. So t can go any number. That's the domain for t. Now let's do some example. So if you plug r of 1, what do you get? T equals 1, so you get the point 230, right? So what is this saying? This is a position vector of a point 230. So 2, and then going go 3, and 0 height is 0. So this is the vector r of 1. So that means this is a position vector of this point 230. Okay. Now here we use another value, r of let's say 2. You get what? 4, 3, 3, right? So at t equals 2, you get 4, 3, and 3. So it's up like here. So this vector is r of 2, which is a position vector of the point 4, 3, 3. So do you see that if you keep plugging values of t, you are going to get some space curve like this, a curve in three-dimensional space. You get the point on this three-dimensional space for t equals 1. You get this point on the space curve, a 3D curve is for t equals 2. So basically this is a vector form. If you trace it, you'll get a curve in three-dimensional space. Okay, so that's the idea. Okay, so and I already said what domain is. Domain means all possible value of t you can get, so that these are all real numbers. Okay, so let's do an interesting example. This is really interesting. Let's do this function. R of t equals cosine t sine t 1. So do you see that x is cosine t, y is sine t? And z is a fixed value, right? Z is, that means what? This parametric equation would be x is cosine t, y is sine t, and z is 1. And t can be any value, but this is a trigonometric function, so t can be from uh, 0 to 2 pi. Okay, so this is the domain, but t can be anything. So how do you draw this?
Is it a sphere?
It's not. It's not. The reason is, do you see the z value is not changing? Then the z value is always fixed. So what is z? Z is, let's say this is 1 here, right? So that means whatever that is, the curve height is 1 of the curve. Now if
Is it like a spiral around the x-axis?
it
Kind of?
is it is not a spiral because z value is fixed. It is 1.
Yeah, like a flat
Yes, so
spiral.
you have done this parametric equation in calculus 1, at least calculus 2, if you have done um, in calculus 1 if you took from NAU. So look at this. What is x squared plus y squared? This is cosine squared t plus sine squared t, and unit is always 1 no matter what t is, right? So that means what? This is x squared plus y squared equals 1 and z equals 1. So what is this saying? Remember we talked about the surfaces. If you just have x squared plus y squared equals 1, that would be a cylinder, right? Because z value can be anything. But here is saying z equals 1. That means it is the intersection of the cylinder with the plane z equals 1. In other words, you get a circle at height 1. That's this guy. Not a good circle. Uh-oh. Does that make sense? Because if you have the x squared plus y squared equals 1, this is a cylinder, circular cylinder. Cylinder would look like what? It will look like this. Now you are intersecting that cylinder with the plane z equals 1. So z equals 1 is this plane, right? It intersects the cylinder at this circle. So this red curve is the uh, given by this vector function, vector value function. Okay. Now, one way to look at them, it would be easier if you do the projection. So what would be the projection? So if you do projection on xy plane, that means what? You just make the z axis 0. So it would be just cosine t, sine t, 0. That means what? This is just x squared plus y squared equals 1. When z equals 0. So that means if you do the projection on the xy plane, what you will get? You will get a circle on the xy plane. That's the projection on xy plane. So by the projection on xy plane, yz plane, and zx plane, you can get an idea of the space curve. That will help you visualize. Okay. Delete this. Okay, so if you project this on let's say xz plane, what do you get? Xz plane. That means we put a y equals 0, right? So this is the cosine t 0, 1. So t goes from what? 0 to pi. And that means what? Cosine value goes from 0 to negative 1 to 1, right? So that means if you project that on xy plane, xz plane is hard to draw. So that will give you this line, isn't it? That goes from what? Negative 1 to 1 from x for x-axis, right? Is that clear? Now, similarly, if you project on xy a yz plane, and that would be what? You make x equals 0, so it will be 0 sine t 1. Again, sine goes from negative 1 to 1. So if you do the projection on the YZ plane, have to draw. It would be like what? This line that goes from negative 1 to 1 parallel to y-axis. Does that make sense? If you just project a circle to the side, the shadow would be just a line, right? From the side, if you have the projection, and if you project on the vertically, then you will get a shadow would be a circle again. Okay. So that's how you visualize sometimes using the projection. Now then we'll do another example. Any question regarding this? Okay, so let's do another example, which is similar, but not exactly same. So sin t, and t. And then t can go anywhere to anywhere. So t is negative infinity to positive infinity. So this is the domain. How do you draw that? You can use projection, but let's just draw few points. X-axis, y-axis, z-axis. For example, if you plug r at 0, what do you get? Cosine 0, 1, sine 0, 0, this is 0, right? What is that point? 1, 0, 0. So this is this point, isn't it? Then plug, let's say, r evaluated at pi over 2. Pi over 2 is like 3.14 divided by 2, right? So that will be what? Cosine pi over 2 is 0, sine over pi over 2, 1. This is pi over 2. So if you look at that point, so 0, 1, and the height is pi over 2. So it will like be here. Do you see how it's, so this is like, anybody knows what it is going to look like? It's going to be a spiral. I'm sorry, helix. Have you seen helix before, right? That the DNA that does double helix, right? So this is the helix. And you can do the projection on xy plane. If you do projection on xy plane, what is that projection? Cosine t, sine t, 0. And you already know this is the curve x squared plus y squared equals 1. So the projection is going to be the curve. This is the projection. Isn't it? If you do the shadow of this curve, that's going to be a circle. But now it will be a little bit more complicated if you do projection on xz and yz plane. So the projection on xz plane would be, um, that means you make y equals 0. And for yz plane, it would be 0 sine t. It's a little hard to draw. So I'm gonna show you from the book what it looks like, the projection. Or usually if you want to get a rough picture, plug few values and you'll see. So this is going to be just x squared plus y squared equals 1. This is fine. This is not hard. This is the circle. But here the t is also changing. So that's the problem. Okay. So I'm gonna show you from from the book. For example, I did sine cosine t and this is negative sign, so it doesn't matter. Can you see it well? Look at this. So this curve, red or pink curve is the helix. Okay. Now if you the project on the xy plane, that's gonna be a circle. If you project that on xz plane, then that's the projection. If you project in yz plane, that's the projection.
It looks like as if you were to like take a sine or cosine function and then turn it 90 degrees as it's, you know, oscillating back and forth.
Not exactly, because the reason, you're right, because look at this. T versus cosine t, right? So it's like what? If z is, let me just write. Uh, yes, just look at, let's say, yz plane. Okay, so look at this. Here what? Y is cosine t and z is t, right? In other words, this is y equals cosine z, right? So if you look at the yz plane, you're right. If you look at the yz plane, can you see it? Yeah, so this is y equals cosine z. That's the cosine curve. And if you look at the xz plane, so x is negative sine t and z is t. So that means what? X is negative sine z. So this is negative sine curve on the xz plane. Okay, so this is negative sine curve. This is cosine curve on yz plane, and this is a circle on the xy. That's the projection for a helix. Any question? So this is like the visualization is the important part here. Okay, let's do an interesting question, the interesting problem. I really cannot draw this by hand. Well, I mean, I can draw it, but you'll have hard time to see. So that's why I'm gonna show you from the book. So consider two surfaces. One is, do you see, what is this? This is Uh, what is this called? Hyperboloid, right? No, it's paraboloid. Sorry, it's paraboloid. It's paraboloid, and this is your cylinder, right? So if you have this paraboloid and the cylinder, where would they intersect? So look at the intersection. Intersection is a curve. You see, this is the curve. And if you just look at the curve is this. Interesting figure. So this is hyperbolic paraboloid, right? This is
Yeah.
hyperbolic paraboloid intersection with a cylinder, a circular cylinder, right? So do we get a curve? Now what we want to do? We want to know the equation of the curve. That means the vector valued function that gives you this curve. Is the question clear what you are trying to do? The intersection is a three-dimensional curve. It's nice curve. Now how do you find that vector equation of that curve? That's the goal. Okay? And there are two ways you can do it. So one is solve for one variable. So here you are solving for, let's say, x. You want to write so intersection of two curves means what? It satisfies this equation and also this equation, right? So you want to write a function that satisfies both of them. So the guess is isolate one variable. That means what? I mean, write two variables in terms of the one variable. So fix one variable, let's say fix x. In this case, fix x. So you want to write y in terms of x and also z in terms of x. Okay, so if you look at the first equation, there is no z. You can write y in terms of x, right? Now, if you look at the second equation, your z can be written in terms of x and y both, right? But we already have written y in terms of x. So just you can replace this y with this x. So if you do that, then your z becomes 2x squared minus x. Okay? So this is plus or minus. So first you take plus. So this is x equals t, y equals positive square root of 4 minus t squared, and z is this. This is one side of the curve, and this is other side of the curve when you took y equals negative. And what is the domain here? Remember domain? Domain means what? You have to get this. This is a real number. How do you get 4 minus t squared as a real number? The whatever under the radical has to be greater than equal to 0, right? That means t squared is greater than equal to less than equal to 4. That means t is in between negative 2 and 2. So that's the domain. Okay, so that means you get two curves, one given by R1, other given by R2. So if you plug that, if you draw it, you'll see that one part of R1, one part of the curve is R1, where y is positive. This is the positive side of y-axis. And other equation y, it looks similar, just y is negative. So it's the other part of the curve, which is the other side of y-axis, negative side of y-axis. Okay. But there is a better way to do it, right? Rather than isolating one variable, writing two variables in terms of one variable. That's one way to do it. And there is another way to do it. When you have um, x squared plus y squared, those kind of terms, is easy to write in terms of sine and cosine. Do you see that if x is 2 cosine, y is 2 sine, then 2 squared cosine squared plus 2 sine squared t is, sine squared plus cosine squared is 1, so that becomes 4. So the parametric equation for x squared plus y squared is 2 is this. X is 2 cosine t, y is 2 sine t, and 0 t goes from 0 to 2 pi. Okay, but now from the second equation, you can write z in terms of x and y. So you plug x equals 2 cosine t, y equals 2 sine t, and use the um, trigonometric identity cosine square minus sine square is cosine t. So it becomes this. So this is a better way of doing it because we don't have to write two parts of the curve. This is a single part. So a curve, space curve, can be parameterized in multiple ways. So this is same curve as the R1, R2 you have seen before. They're the same curve, but they look different. Okay? Any question on it? Yeah, so let me show you the problem set. Can you see the problem set? So I'll talk about the problems quickly. If you have questions, please feel free to ask. First one is asking about domain. Again, domain means what? Find the values of t for each of them are real number. I already discussed when this is going to be real number, right? This means 4 minus t squared has to be greater than or equal to 0. For sine t, t can be anything. What about for ln? Ln curve looks like this, right? So that means ln is defined only for positive values, right? So that means whatever inside ln, that has to be positive. Now use this fact and this fact to get a value of t that satisfies both. That would be a domain. You should be able to do the rest. And problem 2, this is like helix, right? But only difference is this is 2. So whatever the work I have shown you for helix, it will be similar. You draw the projection on xy, yz, and zx plane, and using that, you try to draw a rough picture of the helix. And it's not exactly helix, but it should be similar. Because this projection on xy plane or here yz plane is not going to be a circle. Can you guess what's that gonna be? Y equals sine t and z equals 2 cosine t. What is the parametrization? You're doing calc 2 at the end, if you have done it at NAU. Let me remind you, if you have x equals a cosine t, y equals b sine t, so that means what? X over a is cosine t, y over b is sine t, and then if you take squared and add them, x over a squared, y over b squared equals 1, right? What is that equation? Anybody? What is this equation on xy plane?
Is it a form of a circle?
No, it is circle if a equals b, but if a is not equal to b, what is this?
It's an ellipsoid.
It is an ellipse. I mean, I'm talking about XY plane. Otherwise, it will be.
Oh, all right.
Yeah. So this is A. This is B. So from here, what do you see? A equals 1, B equals 2. So this is also an ellipse on YZ plane. So I gave you enough hint.
Are you asking what it's gonna look like?
Yeah, you need to get projection curve. So on the YZ plane, it is gonna be an ellipse.
Well, for one, isn't the t's in the x value for your original equation? So it's gonna
Yeah,
be like a
but look at this.
sideways.
It's talking about projections,
Oh, okay.
projection curves on the coordinate planes. So I'm discussing when you project that curve on YZ plane, what is that looks like in YZ plane? In this plane, YZ plane.
Is it gonna be an ellipse that doesn't move and
Yeah,
it's
it
gonna
is
be
an
vertical?
ellipse. I mean, it is an ellipse. The ellipse would have this form, so it will look like something like this on YZ plane. Or you can draw YZ plane separately. Right? Okay, I gave you enough hint for that problem. And then you have this matching question. You have uh, the curves and the figures. The idea is when you have sine and cosine, that the projection on that, for example, this one, cosine x is cosine, y is sine. That means x squared plus y squared is 1, right? That means its projection on xy plane is a circle, whatever that curve is. So that means what? That will eliminate a lot of possibilities from these choices. Okay, that's how you're gonna identify the curve to um, equation to curve.
How do you want us to show work for that?
Yeah, you just go give a little justification as I said that x squared plus y squared equals
Yep.
1. That's the projection of curve in B on xy plane, something like
Okay.
that. Yeah, some kind of justification. I mean, the answer is already given. If you just write the answer, you don't get any credit. And problem 5 and 6 are similar. Is basically asking the intersection curve between two surfaces. One is a cone, other is a plane, right? So the picture would look like what? So this is I'm talking about 5. So it's like this, right? Cone. This is the cone. And the plane z equals 1 plus y. That means this is uh, a line. If you do projection on yz plane, it is a line. So something like this. Yz plane. And x can be anything. So it's like, so your intersection is going to be like something like this, right? Then you need to find the vector function for that intersection. And one we can do, we can write, um, in terms of one variable. Z is already in terms of y. Z is also in terms of y, x and y. Then you have to write x in terms of z, x in terms of y. You can think about z squared is x squared plus y squared from here, right? So you can write y in terms of z and x in terms of z, or z is free variable, or right, choose one of them as free variable. That's what I'm trying to say. That's one way to do it. And what the last one, you use this cosine sine business. You can write x equals cosine, y equals sine, right? And then z is clearly from here, you see. All right, we have 10 minutes. Any questions? This is very simple section. Then there are not many, information you can get from this section, but it's mostly about visualization. How do you visualize a space curve? Mainly when the space curve is the intersection of two surfaces. Questions? Thirteen point one. Any question? Because next time we'll do vector valued function and the calculus on them. That means you are taking limit, derivative, and integral. And the idea is very simple. You take derivative at, at t at some value, you're doing component wise. That means, yeah, let's share a screen quickly. So if you take limit t approaches 0, let's say of r of t, and r of t is a function f of t, g of t, h of t. How do you take limit t approaches 0? The idea is the one line idea. If you remember this, you don't have to memorize anything. Component wise. I mean, if you're taking limit of the vector valued function, you're taking limit each component separately. If you want to take derivative at t, that means what? You're just taking derivative of each component separately. If you want to integrate vector valued function, you are just integrating each separately, component wise. 13.2 is very simple. So read about this. I will discuss that on Monday. And I'll try to give you a problem set on that before Monday. So by the way, I don't know if I can mention that before. So when you say that R is a function of vector valued function, R is a function of t, sometimes t is thought as time. Why that? Why is that? Because at each value of t, you get a point on the space, right? That means what? If you can think about a particle is moving on the three-dimensional space. At each value of t, you get a position, right? So that's why t is thought as time. And that is a trajectory or the phase curve of that particle with respect to time. Because x, y, and z are changing with time. Questions? So you have a wave work on this on Sunday night also, right? And also written problem set 5 and 6. You have total how many problems? 14 problems, but we discussed many of them in class. So you should not have hard time. So if you do like 9 out of 14 problems correct, you'll get full credit. Is it doable? Because you are not doing this 9 problem independently. You already talked about many of them in class. You have to just, you have to just nicely write it with justification and steps. Questions, comments? Oh, by the way, I forgot to mention that. Probably I did. I don't remember which section I discussed. So in wave work, wave work is free. You don't pay for wave work. So the downside of that, sometimes some problem might have bugs. So if I catch it, if I fix it, that is good. So most of the problem is right, that's not a problem. But if you feel like you did it 100% correct, but still it is giving you wrong answer, please contact me because I have to report the bug. That's the downside of the free stuff. It's done by mathematician. It's not done by amateur. The problems are done by created by mathematician. But still, if you write coding, you make a small mistake and that might cause a bug. So, but because of that, if you get most problem correct, then you'll get full credit for web work. So you don't have to worry. For example, if you get 95% of web work problems correct, you will get full points for web work. Is that reasonable for you?
Yeah.
So that means if you miss one problem here and there, that really doesn't matter. So do not spend like sometimes I get email that I spend 1 hour on this problem. Please do not do that. You cannot have 1 hour for one problem, at least for web work, So do not do that. That's not a good strategy. And sometimes you do not understand the content and then you struggle. That's a different thing. But you understand it and you know it's correct, but still web work is messing with it. Then send me an email right away. Click on that email instructor button and I will see it. But anyway, if you do mostly correct in web work, if you get 95% correct, I'll give you full points for web work. So do not spend unnecessary time on web work. If you miss one problem here and there, it's perfectly acceptable. At least you're grade wise. Okay? Questions, last minute question, we have 1 minute. All right, guys, keep working on the problem set and the way work. I'll see you next week, Monday. Have a good weekend.